Hello everyone, thank you so much for joining my talk today. In this session, I'd like to introduce our project, the SysBumps attack, a microarchitectural side channel attack on macOS Breakfast Silicon. So, my name is Herin Chang, and I'm a PhD student at Korean University. My research focuses on microarchitectural side channel vulnerability and system security. This project is joint work with my colleague Taehoon and our advisor, Professor Youngju Shi. So let's talk about Apple Silicon. As many of you know, Apple Silicon is Apple's custom-designed ARM-based system chip. In recent year, Apple moved from the x86 processor to their own ARM-based Apple Silicon. This shift is pretty big deal, but with a new architecture comes the important question. How secure is it? And more importantly, how does this vulnerability behave in this new environment? Those questions were a starting point for our research. We decided to explore the potential for microarchitectural side channel vulnerability in macOS environment running on Apple Silicon. Specifically, we focused on well-known security mechanism, kernel address-based layout randomization, or KASLR. The result of our research is SysBumps, an attack that successfully bypasses the kernel address-based layout randomization on macOS Breakfast Silicon. To the best of knowledge, this is the first attack to break KASLR in macOS Breakfast Silicon. This attack leverages the speculative execution within the system code combined with a TLB-based side channel technique. This approach allows us to validate arbitrary kernel addresses in a new way. Before diving into the details, here's the outline of today's talk. First, we will provide some background to help you better understand our attack. Next, we will discuss how previous microarchitectural side channel attack successfully compromised KASLR. We will then explore the challenges of performing this attack on modern processors, including unique difficulty posed by Apple Silicon. From there, we will walk you through our approaches to addressing these challenges. Finally, we will present the SysBumps attack, including a demo to showcase how it works. After that, we will discuss possible countermeasures to mitigate this attack and leave the presentation with the key takeaways. Let's start with the tech background. Microarchitectural side channel attack exploit the inner working of the CPU to infer its internal state or behavior. This attack takes advantage of how processors share and manage resources such to extract information that should remain private. Spectre and Meltdown are well-known examples of such attack. This attack targets specific processor resources such as caches, TLB, branch predictor, and execution unit. So by carefully observing how this component behave, attackers can bypass traditional security boundaries, such as those between user applications and operating systems. Specifically, they capture subtle change caused by the interaction between the CPU's hardware design and operating system's behavior to extract sensitive information. Next, KASLR. As you may know, KASLR is widely used security mechanism designed to make it harder for attacker to predict the exact location of critical data structure or code in memory. This means that in an environment where KPTI KASLR is applied, attackers must first figure out the exact location of the kernel to proceed with an attack. And this process is what we refer to as breaking KASLR. To break KASLR, we need to understand how it's implemented. Actually, the kernel isn't placed completely at random. Instead, it is loaded at aligned addresses within predefined range that is reserved by operating system. For example, operating systems like Linux and Windows load the kernel into one of these predefined range. So if we want to locate the kernel, we can systematically validate these aligned addresses within reserved lanes to infer exact location. And microarchitectural side channel attack targeting KASLR often use this approach to determine the kernel's location. This attack typically leverages the TLB or translation local-side buffer to carry out their operation. So what exactly is the TLB? The TLB is basically a type of cache that helps the system handle address translation more efficiently and plays a critical role in speeding up memory access. When accessing memory, the system uses a virtual address, which must be translated into physical address before memory can be accessed. However, this process can be time-consuming. To address this, the TLB store recently translated virtual to physical address mapping. This allows the system to quickly retrieve the mapping from the TLB when accessing the same address again without performing full address translation process. As a result, memory access is significantly faster, greatly improving efficiency. So when we access memory using virtual address, if the corresponding mapping is already stored in the TLB, the system can quickly perform the access. This is called a TLB hit. On the other hand, if the mapping is not in the TLB, the result in a TLB miss, and the system must perform the address translation, which makes memory access slower. There are two key points here. First, the TLB only stores translation ledger for valid address. If a virtual address is not mapped to physical memory, meaning it's invalid, its translation ledger will not be stored in the TLB. Second, the difference in access time between a TLB hit and TLB miss can be exploited to infer information about the system. So now that we understand this behavior, let's see how microarchitectural side channel attack uses it to bypass KASLR. Traditional attack use a kind of oracle, which basically take a kernel address as an input and it return it's valid or not. This oracle typically rely on behavior of the TLB. For example, if we access target address V and V is valid, the address translation happens successfully, and the result is cached in the TLB. So next time we access V again, it can be done quickly because the address translation ledger already stored in the TLB. On the other hand, if V is not valid, the translation ledger won't be cached. So when we try to access V again, the address translation has to happen all over again, making it noticeably slower than accessing a valid address. This timing difference let us figure out if an address is valid or not. So by checking all possible kernel-based addresses, we can eventually find the correct kernel-based address. This is possible because kernel space and user space are mapped into the same address space. In other words, they share the same page table. So by cleverly suppressing port using prefetch instruction, TXX, and so on, we can create an oracle for the kernel address space. To prevent this attack, modern operating system use a mechanism called kernel page table isolation, or KPTI, which separates the page table for kernel and user mode. This prevents any address translation for kernel space when running in user mode, which means there's no way to access the kernel space anymore. As a result, we can't create the distinguished oracle as we could before. So what challenge must be overcome to build a distinguishing oracle in this environment, and how does the macOS for Apple Silicon complicate these challenges? First, we have to trigger address translation for kernel addresses in user mode because we need to load the kernel address mapping into the TLB. However, as we discussed earlier, modern operating system, including macOS, now apply the KPTI. This means that address translation for kernel addresses can no longer be initiated from the user mode. And then, even if we manage to trigger address translation for kernel addresses, there's another challenge. We can use timing differences to check if the kernel address is loaded into the TLB like we did it before. This is because the TLB now includes something called Address Space Identifier, or ASRD, which ensures that mapping from the one address space cannot be reused in another. We KPTI, because the kernel and user address space are separated, the kernel and user each are assigned different ASRDs. So even if an attacker somehow managed to trigger a valid address translation for kernel addresses, it's still happening in kernel mode, meaning the ASID for the kernel address is different from the one used in user mode. As a result, when the attacker accesses it again, a TLB miss occurs, making it appear as though the kernel address has been loaded into the TLB. In summary, to create a distinguishing oracle, we need to do more than just trigger address translation for kernel addresses. We also need a reliable way to verify whether the kernel address is actually loaded into the TLB. Now, onto the binary challenge. As we talked about earlier, microarchitectural side channel attack on KASLR usually rely on pressing all possible kernel-based addresses. So to efficiently perform a KASLR breaking attack, we need to detail the information about how KASLR is implemented. However, unlike Linux, Windows, and even Intel-based macOS, no such information is publicly available for macOS running on Apple Silicon. To make this attack feasible and efficient, we need to figure out details about the kernel address, range, and alignment size. Now that we've identified the key challenges in breaking KASLR on macOS for Apple Silicon, I'd like to discuss how we approach these problems. First, we start thinking about how we could trigger address translation for kernel addresses in user mode and in environment where KPTI is applied. And we turn our attention to system call. System call are handled in kernel mode and take user input. What's more, even if we provide invalid input like kernel addresses, some system calls don't throw forward. They just return general code. This means that if we can get the system call to access the kernel address we gave as input, we can still cause the TLB state change depending on the validity of the address, just like in previous attack. Now, you might be wondering, is this really possible? After all, system call likely has some kind of input validation process already in place. But our answer is yes, because we found a Speculative gadget within macOS for Apple Silicon that allows us to bypass this input validation process using speculative execution, letting us access those kernel addresses. Speculative execution is an optimization technique used by modern CPUs when they are unsure about the direction of the brains. The CPU makes a guess and runs the instruction ahead of time based on past behavior. If the guess is correct, it boosts performance. If it's wrong, the execution is rollback as if nothing happened. But the key point is that even though it seems undone, the ledger still leaves traces in microarchitectural components like cache or TLB. And that's exactly what an attack Spectre exploits. Spectre leverages the fact that the speculative execution is based on historical patterns. An attacker can intentionally mistrain this history to force the CPU to speculatively execute a specific range. If the target data is accessed during this speculative execution and loaded into the cache, the attacker can extract it using the technique like cache side channel attack. And this is the gadget we discovered in macOS for Apple Silicon. It mostly found a system code that takes a string pointer as an argument like CHDIR. The gadget validates input address path specifically through the copy validate function on line 2. And this function mainly checks the address range. So if the address is valid, it passes through the conditional range on line 4, and the big copy insert function is called where the path is accessed. However, if the kernel address is given as the path value, validation fails and the function exits through a return instruction in the conditional range. But here's where speculative execution comes into play. Using speculative execution, we can transiently execute the bcopy insert function, even when we provide the kernel address as input. Specifically, the conditional range on line 4 won't know its direction until copy validate finishes. This uncertainty makes speculative execution inevitable at that point. So first, we train the conditional range by calling the system call a few times with a valid user address. Then, when we provide the kernel address as an input, the branch still predicts first, and the bcopy insert function is transiently executed. As a result, the kernel address is accessed within speculative execution, leaving traces in microarchitectural state, particularly in the TLB. Now that we've addressed the first challenge, the next step is to check if the kernel address is cached in the TLB. To achieve this, we use a technique called prime proof, which is a type of cache side channel attack. Prime proof lets us import changes in the cache state indirectly, making it possible to determine if a specific address is loaded into the cache. Specifically, an attacker payload cache with their own data and later check if the data is still there. This reveals whether the specific address was accessed. So since the TLB is a kind of cache using this method, we can check whether an address free is loaded into the TLB. Here's how it works. The TLB is organized into set, and each address is assigned to a specific set based on part of its address bit. So first, we identify the addresses that map to the same set as the target address. We need to as many addresses as the size of the set. And this group of addresses is called the eviction set. Next, we access the eviction set to fill the corresponding TLB set. This step is called prime page. And then we access the target address free. If the free is valid, the TLB loads the translation ledger evicting entry from the eviction set. So when we access the eviction set, the evicted entry causes TLB misses, resulting in longer access latency. On the other hand, if it is not valid, the eviction set remains intact in the TLB. So accessing it again results in relatively lower access latency. This final step where we re-access the eviction set is called the probing phase. By measuring the probing time, we can determine whether the target address free is valid or not. To use this technique, we first need to create the eviction set, but this requires detailed knowledge of the TLB. Because we need to know the number of sets and their size in the TLB to figure out which address bits are used for indexing. That is, how each address is assigned to a specific set. To gather this information, we conducted reverse engineering on various M-series Apple Silicon CPU, as shown in this table. We reverse engineered the TLB structure using performance counters, which are CPU event measurement tool. Specifically, we analyzed the TLB details by measuring TLB miss event with these counters. By accessing memory with various strides, we captured miss event and uncovered detailed information about the TLB structure. Here's what we found. The TLB is organized into two levels, the L1 TLB and the L2 TLB. The L1 TLB is divided into two parts, DTLB for data and ITLB for instruction. Additionally, we discovered that the L1 ITLB is further split into separate user and kernel TLBs. Meanwhile, the L2 TLB served as a unified cache supporting all L1 TLBs. In our attack, we don't execute the target address as an instruction, we just rely on accessing it. For this reason, we focus on performing prime proof at the L1 DTLB and L2 TLB level. Now that we've addressed the first two challenges, let's talk about the final one. Unlike Linux and Windows, there's no publicly available information about KASLR implementation of macOS for Apple Silicon. To uncover this, we conducted an experimental analysis. We collected the kernel-based address through the 50,000 reboot across 5 different devices used for reverse engineering. Through this process, we found that the kernel-based address falls within the range shown in the slide and are aligned to 60 kilobyte boundaries. This means there are roughly 32,000 possible kernel-based addresses, and we use this finding as the foundation for our attack. So, in the end, this approach allows us to overcome the challenges. This approach allows us to overcome the sorry. So, in the end, this approach allows us to overcome the challenges and create a distinguished oracle in this environment. The oracle consists of 4 main steps. First, we start by training the gadget we talked about earlier. To do this, we invoke the system call using a valid user address. Then, we access the eviction set to fill the corresponding TLB set. The eviction set can be constructed using reverse engineered information. Next, we invoke the system call again, but this time with the target kernel address. Due to the training in the first step, the system performs a speculative execution, leading to transient access to the target kernel address. Then the TLB state changes only if the target address is valid, otherwise it stays the same. Finally, we re-access the eviction set and measure its access time. If the access is slow, it means the target address was loaded into the TLB, evicting entry from the eviction set. This indicates that the target address is valid. On the other hand, if the access is fast, it means the target address was not loaded into the TLB, and entire eviction set remained tagged into TLB. This shows that the target address is valid. This shows the eviction set probing cycle for each level of the TLB. At the L1 level, we observed that difference of about 40 cycles depending on the validity of the address. While at the L2 level, the difference was around 400 cycles. While due to the smaller cycle at the L1D TLB, we found that performing the attack at this level resulted in lower accuracy. Therefore, in our attack, we performed the prime proof at the L2 level. In addition, we investigated which system code could be used in our distinguishing oracle. Since our attack requires providing a kernel address as an argument to the system code, we focused on system code that takes an address as an argument. Through this investigation, we identified 25 system code that could be used in our attack. Most of these system code take a string address as an argument, and upon analyzing their code, we confirmed that they include the SysBumps gadget. Now, using this attack parameter, we can check the validity of all possible kernel-based addresses to find the kernel-based address. First, I'd like to show you a demo of our attack. Here's the actual process of our attack. As you can see, our attack is able to locate the kernel-based address in just 3 seconds. Next, let's take a closer look at the probing cycle for each address. Alright, let's see it. This is the graph we just saw in the demo, focusing on the legend where the kernel is loaded. We can see a specific legend where the consistently high cycles are measured. That's where the kernel is loaded. In other area, the cycles are alternated between high and low, which we suspect is due to noise introduced during system call execution. I think this makes sense because when a system call is executed, it often leads to TLB entry being replaced. However, despite this, the consistently high cycle in actual kernel legend allows us to accurately determine where the kernel is located. We evaluated the performance of SysBumps using all exploitive system calls across 5 different devices. In total, we conducted 1,000 attacks, lifting the system every 10 attempts to reset the kernel-based address. The ledger shows some difference in both speed and accuracy depending on the system call, but when we average the performance of top 3 system calls, we found the kernel-based address with 96% accuracy in under 3 seconds. So how can we stop this attack? The simplest way is to prevent the speculative execution within the gadget itself. To achieve this, we can use branch instruction to control the execution order of the instruction. In simple terms, it ensures that any instruction after it won't learn until all the one before it are completed. On ARM architecture like MP Silicon, examples of such instructions are DSP and ISP. By placing these instructions before the conditional branch, as shown in the code on the right, the branch will only execute after copy validate function has finished it. This makes it significantly harder to exploit speculative execution within the branch. Another approach is to reorder the code to ensure that the big copy insert function cannot be executed during speculative execution. Speculative execution only runs instruction up to the point where the condition is reserved. This means that there is a limit to how far speculative execution can go. By rearranging the code so that the address validation logic and the actual access that address are placed far apart, we can make it much harder for an attacker to exploit speculative execution. This method can be applied at the software level, making them relatively easy and quick to implement. However, they have a certain limitation. They only work for identify the gadget. So attack that exploit potential gadget we have identified cannot be mitigated using this method. At the hardware level, one possible mitigation is to cache the ledger of address translation for invalid addresses in the TLB as well. By doing this, when a kernel address is accessed, the eviction set entry will be evicted, regardless whether the kernel address is valid or not. This removes any difference in proving cycle, making it impossible to infer the validity of the address. Another approach is to separate the TLB into user-only and kernel-only sections, similar to how the L1I TLB is divided. With this setup, an attacker performing prime proof would only interact with the user TLB, while kernel address cached during system call would reside in the kernel TLB. This separation eliminates contention between user and kernel TLB entries, making it impossible for an attacker to determine whether the kernel address has been cached in the TLB. This hardware-level mitigation have the advantage of addressing potential vulnerability as well. However, their implementation can be a little more complex and costly compared to software-based solutions. We have liberated our finding on SysBumps attack, including this mitigation strategy, to Apple. Apple has informed us that they plan to address our report. Also, we plan to share a proof of concept for our attack on GitHub. Currently, there's no code available in the repository, but we will make it public as soon as the vulnerability is patched. In conclusion, here's the key takeaways from our research. We explored a new microarchitectural sidechain attack called SysBumps, targeting ARM-based Apple Silicon environment. Through this attack, we demonstrate that it is possible to compromise KASLR on macOS for Apple Silicon. As far as we know, this is the first attack targeting KASLR on macOS for Apple Silicon. And SysBumps attack leverages the combination of a speculative vulnerability in specific system call and side effect of address translation on the TLB. This new approach enables attacker to bypass the robust security mechanism of latest macOS system. Finally, we discussed potential gadget and potential countermeasures that can be applied at different levels against the SysBumps attack. That concludes my talk. Oh, I'm almost out of time, so I won't be able to take questions here. But please feel free to email me or reach out through the Black Hat app. Thank you for your attention. Thank you.